When I was younger, I always wondered how video games could take 3D objects and somehow display them realistically on my 2D screen. So I thought there must be some kind of way to take 3D space and convert it into 2D space, but still preserving perspective and making everything look nice. And now I've actually figured that out. So I thought, if you've ever wondered that, or if you're curious, I want to show you how that works. So the first thing we need to do is define what we're working with. So here are the things we're dealing with. One is called world space and the other is called screen space. And world space, that's what you can call 3D. So that's 3D, and screen space, that's 2D. And that means that world space, the coordinate system has one extra value than what we're used to with normal 2D coordinates. So world space is three-dimensional, meaning you need three numbers to represent a coordinate in that world. So let me try drawing something. So this is a cube in world space. It's a little hard to illustrate because this is 2D paper, but maybe this like 3D cube that I made can give the idea. Of course, you're looking at this through a 2D screen, so it's not maybe helping that much. But yeah, let me draw the axes of world space. So here we have a coordinate system for what I call world space. And as you can see, we have these three axes. Y and X are kind of what you're used to. So Y is vertical and X is horizontal. But then Z it's really hard to draw, but it kind of goes like out and in of the page, if that makes sense. So this pen right here is sort of X moving in X right now, if that makes any sense. And so this would be X and this would be Y. Yes. So that's compared to screen space. So this is screen space, and I drew it with like an actual screen to kind of represent, but here you can see we only have two dimensions. So we have the normal y-axis and the normal x-axis. And this is maybe misrepresenting it a little bit, or it depends, because there are a lot of ways that you can represent your screen space in relation to your screen. But what we're going to be doing, just because it's the easiest to do, is we're going to kind of make it relative, our screen space. So let me draw that. So this is sort of relative screen space, you could say. So what we have is the middle of our screen is 0, 0, and then everything can range between +1 and -1. So all the way over here, X is +1, and then over here on the left, X is -1. And same if you go up, then Y goes towards 1, and if you go down, then Y goes towards -0. So this random point is +½ X and -½ Y, right? And the reason we're doing this is because this is really easy to adapt to any screen size. So we can do our calculations regardless of what screen size your screen actually has. So let me write an example size. So this is like a real screen size with some very large numbers. But to convert this one to this one is very, very easy, you can see. So it's just like multiplying and maybe offsetting a bit depending on how you draw to the screen. But yeah, so that is the two spaces we have. And what we need is a way to go from world space into screen space so we can display it on our screen, right? But the problem is that we're kind of losing information here because world space has an extra coordinate, or like an extra number in its coordinate for a given point. And so if we take a point and want to convert it to screen space, we're kind of losing a value. So what we want is, if we can somehow incorporate this C value, set value, into this X and Y to maybe somehow like incorporate that value into them so it looks realistic with perspective when you have like multiple objects and maybe one is in front of the other, so it should appear bigger. Then, so that's what we're looking for. So we're looking to get rid of the set value, but somehow like bake it into these two to translate the 3D into the 2D. So there are multiple ways of doing what we want, which is going from world space into screen space. So one is called an orthographic projection. That doesn't look very realistic in relation to perspective. There's something called ray tracing, which is like a totally crazy thing. But then there's something called a perspective projection. And that is not very difficult to do, and it also looks quite realistic. So I'm gonna show that to you. Great. So I just drew a whole bunch of stuff. But this is essentially illustrating the important parts of a perspective projection. So this thing right here is called the viewing frustum, which is basically, I hope you can sort of see the shape of it. It's meant to be like a pyramid on the side. Yeah, that's like the viewing frustum. And we have some more labels here. So one is this little point down here where all the lines of the viewing frustum, or like the pyramid, meet. And that is called the camera. Or you can kind of think of it as like your eye. Then there is this thing, this sort of rectangle right here, which is called the near plane, or you can kind of think of it as your screen, right? And then there's this rectangle, this is called the far plane. But for our example, we're actually gonna ignore that. Usually video games and stuff, they have this to limit how far you can see, so it's not computationally super expensive, so you can see like infinitely. But in our example, we're gonna be seeing infinitely. But if you look at this, this is basically achieving what we want, or it sort of represents with your screen perspective, if that makes any sense. So this space in front of the screen expands the further away it gets. You can see it sort of keeps expanding, meaning that further away you can see more stuff. And of course, if you can see that more stuff, that stuff has to be smaller in order to fit, right? So it's sort of a representation of things getting smaller the further away they are. And it turns out that we can actually use this sort of model to, in a way, look through this screen, or take things in front of this screen in the world space and see where they cross in the screen that I've drawn here, or the near plane. So I'll illustrate that in a bit. But basically think of this viewing frustum as something that expands when you get further away, meaning things have to get smaller in order to fit. So what I'll show you now is the perspective projection, or like the viewing frustum, all of this from the side, because that will make things a lot more clear. So here we have the model for the perspective projection as seen from the side. So this axis, which is normally if you draw a coordinate system like this axis is the x-axis, but now it's the z-axis. So as things move this way, they get further away, if that makes any sense. And that works with how these lines are drawn. So if you remember from the pyramid, how when things are further away, you can see more stuff. And that's what these lines represent. So that's also called the field of view. So these lines are the field of view. And as you get further away, you see more stuff. And this line, this is called the near plane, as we saw, also known as your screen. And the set value for that is what we're gonna call near, or we're also going to write it as just n, just for short. And then we have a few other values. So we have this angle, which represents the angle of your field of view. So that can be bigger or smaller. That's something you sort of define when you define your perspective projection. And then we have the y-axis here. We have a few values marked on it. So one is here, where y is equal to +1. And if you remember from relative screen space, this works with how we defined like our screen space. So this is 0, and this is +1, and this is -1. And by the way, this line right here in the middle, that wasn't in the last picture, but it doesn't really matter very much, but it becomes helpful to know where the axes are. Yes. So what the goal is in a perspective projection, you can think of it as having objects out here in world space, drawing a line from, like, let's say there's a point out here in world space. We want to draw a line from that point to the camera right here and find out where it crosses on our screen or our near plane. So let me illustrate that. So here we have these two objects, and we're imagining that they are in 3D space, although we can only see them from the side. But I've focused in on 2 points on them each. So these like corner points. And basically what we're trying to find out is how would these points in 3D space look on our screen. And what we do is we draw a line from those points to the camera. And then what we look at is our screen, where do they cross? And then we see something really interesting, which is that even though these two objects have the exact same size, where they cross is quite different. So the one closer crosses here and here. And then the one further away, its points cross here. So if you can imagine this being drawn to the screen, you can see that this one that's closer gets drawn bigger, and this one that's further away gets drawn smaller. And so that way we're kind of encoding the values of the z-axis, which we're losing when we go into screen space, but we're figuring out where they cross in screen space, if that makes any sense. But it turns out that like this is a perfectly valid way to do this. It's just taking these points, figuring out, drawing them to the camera, and figuring out where they cross. That is really all you need to draw 3D onto 2D. So that's all we need to figure out now, is like, how can we make a general formula for figuring out where they cross? And so we just need some like basic trigonometry. So I'm going to explain that. You can skip that if you want, But the end result is just some formulas where you can give a 3D coordinate, and you can find out where it crosses on your screen, and that is actually like the 3D point getting converted into a 2D point on your screen, so perspective is preserved. So now we're ready to get into the math of like coming up with the general formula to take 3D points into our screen space, into 2D. So I'll start by writing some formulas that we need. Great, so I wrote up a bit of stuff here. So here's a right triangle, and I labeled it just with like the letters. So this is the hypotenuse, the, I think, opposite, and the adjacent. And then I wrote up like the definition of the tangent, which is like the ratio between the opposite and the adjacent. So that is important. Then the reason that this is important is because we have two right triangles behind our screen. So that's what we're starting with. And so if we focus on like just one of these, what do we know about it? I'll write that up now. Great. So we know that the angle is our A value divided by 2, because we took like half of this to get a right triangle. Then we know the length of the adjacent, and that is the near value, or how far away our screen is from our camera. Then we know the height of the opposite, which is 1, because that's how our screen space works, our relative screen space. So we know all these things. And yeah, so let me write up something else. Great, so now I'm using this definition of the tangent, and I'm putting in the values that we already know from our right triangle. So if we put in the angle here, we should be getting 1 divided by n, n, which is how far away our screen is. And if we move this stuff around, we get a definition of just n. So now I move some stuff around, and we now have like just a general definition of n. So you can put in an angle and you're going to get an n value. So that's going to make our life a lot easier. Now we need to start thinking in terms of these points and where they cross. And to do that, we find another right triangle. So let me draw that out. So what I've drawn here is I've zoomed in a little bit on this area, and I've taken an object, and this is again our screen, and this is the camera, and they also form a right triangle. I've drawn it a bit badly here, but yeah. So this point here, now we're focusing on the y value. So the y value of this point is just going to be y. We're just calling that y. And then where it crosses, we're going to call that yp, like the y point on our screen. Then we can kind of look here and we can see there are actually 2 right triangles. So there is one here with yp and n for our near, and then there's another one here with y and z, so whatever this z value is of this point. So we have 2 right triangles inside each other with the same angle. So one is, you could say, almost like a scaled up version, or their kind of proportions are supposed to be the same. So we can use the rule of similar triangles to write out a statement, or we can, let me write it out. Great. So what I've written now is that the opposite, which in this case of this small triangle, its opposite divided by its adjacent should be equal to the bigger triangle's opposite, which is y, divided by its adjacent set. So their kind of ratio should be the same, and that's why I can say that they're equal to each other. And so if I move some stuff around to get a definition of yp, because that's what we're looking for here, let me do that. Great. So what I did now is I just multiplied n on both sides, and so we end up with a definition of yp, and that is what we want basically. And it has n here, which we have defined like this. So we can actually change this up to include our definition of n. Great. So I moved some stuff around once again just to make it prettier. But now we have a definition of yp. And that is all we wanted. So if we look at this, what we supply is the ankle of our view frustum, and then a y and a z, and then we get another y. And that y, the yp, is in screen space. And it turns out that if we would do this exact same thing like we did here from above, we would get basically the same definition of xp. So let me write both of them down. Great. So here we have the definition of xp and yp, basically the point on our screen. We have like definitions from that, and what you sort of give these definitions, what you input is the x of the 3D space and the set value, so like the depth, then you get a new x. And for y, you supply the y of the 3D space and the depth, the set value, and then you get a new y. And this is what we wanted. So this is what we set out to do to begin with. So we went from 3D space, world space, into 2D space, but we bake in depth information to preserve perspective. So we're done now. Like this is what we wanted. I'll do a code example now to show this in action, because I think it's quite boring just looking at it on paper. So if you want to see that, you can stick around. So here we have some TypeScript code to show an example of the math that we just did. There's also a bit of HTML and CSS, but yeah. The first thing we define is the faces of our cube. So we're going to be drawing a cube, and we define the points that make up the face of the cube. And we only define like the bottom and top and front and back, not any of the sides, but this is because we're only going to be drawing the outlines of the cube, so we don't really need all the faces. Then we define some constants, so this is the width and height of our canvas. Then the cube distance, so we're going to be pushing away the cube after we rotate it, just so we're not standing inside it, which these coordinates actually would do. Then we define a line width, and we do just some setup of the canvas. And here's our transformation function of transforming 2D to 3D. So you input an x or y and a set value, and then it calculates the angle in radians of the field of view, and then does the formula that we defined. Then we have this draw function, and we have an event listener listening in on the mouse move. So the reason we have this is that I wanted this to be interactive. So you can actually rotate the cube based on your mouse position. We also have an initial draw of the cube. So maybe I should show the rotation function. So that's just a rotation matrix that I took off Wikipedia just to rotate in 3D. Then we have a simple polygon drawing function. And so this is the draw function. We first clear the canvas, then we calculate this ratio, and then we transform our faces into 2D faces, basically. So we start by rotating the cube, then we push it away with our distance, then we transform 2D to 3D, and then we stretch it to fit our canvas and also offset it because you draw to a JavaScript canvas from the top left. And then we just draw the polygons of the faces. So this is the result. So it's this interactive cube, and we can see perspective. Actually, if I do like this, we can see that the face that's closer by appears bigger than the face that's further away. So yeah.